2 days ago, 3B1Brown posted this puzzle where we have bacteria on a grid which can replicate by placing its clones at adjacent points in the up and right direction. This replication can only occur if those two spots are free. In other words, two bacteria cannot exist on the same point. The puzzle was, if we have a 4x4 grid, what is the minimum number of replications that are needed in order to clear that 4x4 grid so that there's no more bacteria at any point on that grid? In order to do this, we can think of it as being on the squares of a chess puzzle because it just makes it easier to think of. So let's say the bacteria starts here. We want it to clear this 4x4 region so there are no bacteria anywhere here. So in order to do that, you could do something, it would look something like this. And then maybe you replicate this one. And then you could do the same thing again. Right? But notice how this one here, this couldn't replicate because it's being blocked by a bacteria here. So as you start doing this, it comes clear that this takes a lot of moves to do. And it's very hard to analyze this just using brute force, because every time we make a new move, another bacteria is added. At first it should seem almost obvious that the bacteria would eventually leave this region. But as you start playing around with this, you realize that maybe it's not possible. Maybe the number of bacteria that is increasing has this effect of continuously preventing the other bacteria from escaping the square. So now the question becomes if this is even possible. To prove that it's possible is easy. All we have to do is find a combination that works. But to prove that it's impossible, we have to be clever. One thing you might think of doing is using what's called an invariant. So finding something about the problem that never changes, a quantity that never changes. So this is often useful when you have evolution is too complex to foresee. If we can find something that's invariant, a quantity that never changes, it can offer insight about the problem by abstracting away the complexity of it. So this is often done with physics, like any conservation law, like conservation of energy, conservation of momentum, angular momentum. It abstracts away the complexity of the problem and it gives you what you want to know. One way you might think of doing this is to assign a number to every square in order to get some quantities involved. So let's say that this square is 1. If the bacteria starts here, when it replicates, it has to go either here or here. So if we wanted the quantity to never change, if our quantity was the sum of all the numbers where our bacteria landed on, we would want the numbers under these two squares to add up to the number under the original square. The simplest way to do that is just to assign half of 1 to each of these squares, because 1/2 plus 1/2 is 1. Then by the same logic, if a bacteria was here and it replicated here and here, we would want these two to add up to this number under this one. So we could, by the same logic, we would have to take another half of 1/2, so a fourth. We could see the pattern. So we keep putting more numbers, numbers that go like 1/2 to the n, under each square until we go out to infinity. So now we can think, what would it take for the bacteria to leave this 4x4 region? That would mean that there would have to be absolutely no bacteria whatsoever in this 4x4 region, and all the bacteria would have to lie outside of it. If the total sum under all the squares outside of this 4x4 region is not greater than 1, then there would be no way for the bacteria to leave this 4x4 region. Because if it did, the sum that we showed was invariant would no longer be invariant, because there would be no way for the bacteria to distribute itself over the region outside the 4x4 square so that that sum remains equal to 1. Because the best we could do is put it on every single square outside that region, and if that sum was less than 1, we know that it could never be equal to 1, because by removing some of them, we would only decrease that sum. You see that this is just a geometric series, right? So we know an infinite geometric series with starting term a has sum 1 minus, or a over 1 minus r, where r is the common ratio. Let's call the sum of just this first row S1. The first term is 1, and then the common ratio is a half. So we have that the sum is 1 over 1 minus 1 half, which is 2. And then if you notice, the next one after this is just S1 over 2, right? 1 half is multiplied to every term in S1. And then the one after that is just S1 over 4, and it goes on and on. So we see we have another, just another geometric series, except this time the starting ratio is, or the starting term is S1, but the common ratio is 1 half. If we sum every number inside this 4x4 region, we actually get a number that's approximately 3.51. So minusing this from 4 gives us a number that's close to a half, so it's much less than 1.
So because we already proved that this sum, this quantity that we showed was invariant, can never change, we know that there's no way whatsoever for the bacterias to ever completely leave this 4x4 region. Otherwise, that sum could not be invariant. So we have a contradiction. So the question was phrased in such a way that I thought there would be a nice finite number, like a counting problem. But I think it was a trick question. I think it seems like the answer is no. There's absolutely no way for this to occur in a finite number of moves. But yeah, that's about it.